All right, we're going to do Chapter 11, Section 1 today, and Chapter 11 is on the chi-square test. In terms of what we've learned this year, we had the normal distributions, then we learned about t-distributions, and now chi-square is going to be its own distribution, completely separate from the normal, completely separate from the t-distribution. So it's going to have some different uses for different purposes. So you can see sometimes we want to examine a distribution of a single categorical variable in a population. The chi-square goodness of fit test is the one that we have a hypothesis, and then we want to see if that seems valid for an entire distribution. We can decide whether the distribution of a categorical variable differs for two or more populations, just like in Chapter 10, we went from one population to two. That's going to be a chi-square test for homogeneity. And in the last is when we work with two-way tables, which we worked with during our probability chapter. It is possible to use the information in a two-way table to study the relationship between two categorical variables. That's a chi-square test for independence. So there's two sections in the chapter. The first one is one population, one variable. That's chi-square goodness of fit. Then we have two populations, one variable, chi-square test for homogeneity. Then we have two variables on one population, chi-square test for independence. So it's going to be basically the same type of situations we did for the last few chapters, but all in the chi-square curve. So we were going to do a example in class where I gave you M&Ms and you would look at the distribution compared to what M&M company claims for the color distribution in a pack, and we were going to test to see if their claim and the actual pack match. So Mars Incorporated makes milk chocolate candies. Here's what the company's customer affairs department says about the color distribution of milk chocolate candies. Basically, this is a claim, like a null hypothesis, and we're going to test this claim. On average, the new mix of colors, M&M's milk chocolate candies, will contain 13% brown and red, 14 yellow, 16 green, 20 orange, and 24% blue. What we have here is called a one-way table. This one-way table summarizes the data from a sample bag of M&Ms. In general, one-way tables are used for one variable, but it takes multiple outcomes. So yeah, we're dealing with one population, meaning one bag of M&M candies. We're dealing with one variable. The variable is the color, but the variable takes many outcomes. So we can't just use a proportion like we did in a one prop z test, because this is not just the proportion of blue. This is the whole distribution to see if it follows their claim. So we have a lot of p-hats. We have a proportion of blue has its own p-hat. The proportion of orange has its own p-hat, etc. So with our old one proportion z test, since the company claims 24% of the bag should be blue, we have a null hypothesis claim of 24 versus what we're looking for is not blue. The problem is in Chapter 9, we could have only done this for one color at a time. In Chapter 11, we're going to be able to check the whole distribution at once. So performing a one sample z-test for each of these proportions is very inefficient. That's why we have the chi-square statistic. So performing one sample z-test for each color wouldn't tell us how likely it is to get a random sample of an entire bag of 60 with a color distribution that differs as much as the one claimed by the company. For this, we learned the chi-square goodness of fit test. The chi-square goodness of fit test is the only test that they teach in Chapter 11, Section 1. Here's how it works. The null hypothesis of a chi-square goodness of fit test should state a claim about the distribution of a single categorical variable in one population of interest. And it's easiest to write it in words typically. H naught. The company's stated color distribution of M&Ms is correct. It's just that simple. Your null hypothesis is that the claim is true. So you say that their color distribution is true. The alternative hypothesis in the chi-square goodness of fit test is that the distribution is Not correct. So, H alternative. The company's stated color distribution for M&M milk chocolate candies is not correct. It's just that simple. You do a correct for a null and not correct as an alternative. You could potentially have written this as numbers. So our null hypothesis could have been the population proportion of blue is 24, population proportion of orange is 20, and so on for all of the outcomes of the variable. And now what the chi-squared test is going to look for is at least one of these is not correct or is incorrect. That's all this test is going to look for. So P sub color, they identify their variable as the true proportion of M&Ms of that color. The idea of the chi-square goodness of fit test is this. We compare observed counts, meaning if you had a bag of M&Ms and counted the colors, that is a sample, that's an observed count, versus what we would expect, meaning they might claim 24% are blue, but our bag only had 60 M&Ms. So you would make an expected count of 24% of 60 to say how many blue you would expect. That's how this works. The chi-squared statistic says, assuming the color distribution that is stated is correct, just like we do with every null hypothesis, for a random sample of 60 candies, 24% of 60 candies would be 14.4 should be blue. Now, your expected counts definitely can be decimals. It is completely okay. And you can see that they have the claim percentage times the amount in the actual sample gets these expected counts. So you end up with each outcome of the one categorical variable with the observed counts and the expected counts. To see if the data give convincing evidence, just like every hypothesis test, versus the null, we compare the observed counts with the expected counts, assuming the null is true. If the observed counts are far from the expected counts, we seek the evidence we are looking for. This is just a visual display, and you can see we see some fairly large differences between observed and expected counts, but we really don't know until we pop this into the formula and get a true test statistic. So this is more just visual. So you can see, for instance, yellow, observed and expected, quite different. But red, not too far off. We're going to look at an overall picture to see if there's true significant difference. So we're going to do the chi-square statistic. Now, this is just like we had a z statistic, then we had a t statistic. We'll have a chi-square. Now, chi-square, chi is a Greek letter. It looks like an x. So it kind of looks like a swirly x squared, chi-squared. And the way it works is you do the sum of every single observed minus expected squared divided by expected. Observed minus expected squared divided by expected. And then you have to do that for every color and then add it all up. We'll show you what it does. This is definitely going to be something your calculator can end up doing. You can see here each color gets its own contributor to the chi-square statistic. So each color, about how far off it is from its expected, observed minus expected, will add and add and add. And as the chi-square gets large, it becomes more rare. The bigger the chi-square, the more rare the event. So the chi-squared measures the distances of the observed counts from the expected counts. Large chi-square values give strong evidence against the null, because we say that the observed counts are far from what you'd expect. Small chi-square suggests you don't have evidence against the null hypothesis. So the chi-square distribution, and then we have to get a p-value, just like every hypothesis test. The sampling distribution of a chi-square statistic is definitely not normal. It is definitely not t. It is its own right-skewed distribution, and because everything gets squared, it's only positive values. So that's why it starts at 0. When the expected counts are at least 5, so what we're seeing here is we're creating our conditions for inference. We're still going to have some conditions for inference here. Then the sampling distribution of chi-squared follows a chi-square distribution, and we're going to have degrees of freedom here again. It's the number of categories minus 1. So like our colors take away 1. The chi-square distribution is a family of distributions, just like a T-curve. You have our number of categories minus 1, and the curve goes from really steep, and then it kind of gets more and more closer to less right skewed as you increase the degrees of freedom. But it always is right skewed, always. So we computed a chi-square for our 60 M&Ms to be 10.18. All of the expected counts, I'll go back, expected counts, meaning all of these, what you'd expect to be in the M&M's bag, needed to be at least 5 to conduct this inference. The smallest we had was a 7. We are good. Since they were all at least 5, and our degrees of freedom is the number of colors of M&Ms, take away 1, we have 5. We get the degrees of freedom 5, chi-square curve. Now, what you see here is if you needed to use a chi-square table, you would see our p-values between 0.05 and 0.1 for our 10 chi-square value. We won't be really using this chi-square table too often, really at all. So our p-values between 0.05 and 0.10, just like always, the whole year versus alpha of 0.05, there's not enough evidence here. So therefore, we fail to reject H naught. That is the only way you should be writing how to go with the null hypothesis, is to fail to reject H naught. We don't have sufficient evidence to conclude the company's claimed color distribution is incorrect. So we still talk about the alternative hypothesis and just say we don't have sufficient evidence for the alternative hypothesis. The company's claim is incorrect. So we go to our carrying out a test, and we know that we have conditions we checked in a planned step all the time. This is the chi-squared goodness of fit test. The data must come from a well-designed random sample or randomized experiment. If you are sampling, make sure the population's 10 times larger than the sample. If you are taking an experiment, don't do this step, and then all expected counts greater than 5. That's it. That's all the conditions for inference. Before we start using a chi-square goodness of fit test, we have 2 important cautions. The chi-squared test statistic compares observed and expected counts. Don't try to perform calculation when the observed and expected proportions of a category, meaning if the company claimed 24% blue, you're not using 24% for this chi-square test. You have to turn that into how many expected candies would be blue. So when checking the large sample size condition, be sure to examine the expected counts, not the observed counts. So make sure when you check that they're all greater than 5, make sure you're checking expected counts greater than 5, not observed counts. So we're going to be at the point now where we're going to summarize the test. So suppose our conditions are met. Our null hypothesis will always be that the distribution of whatever categorical variable you're looking at, like the distribution of colors of M&Ms, is correct. And then the alternative will always be like the distribution of a categorical variable, like the colors of M&Ms, is not correct. You're going to want to know how this is made, because sometimes you might have to do this on your calculator where you do the observed minus expected. You'll put these in a table. You'll square it. We'll divide by the expected and we'll add it up. It's not that hard to do this on a calculator. So when the sum over k categories, then we get our degrees of freedom, which is categories minus 1, and you get your p-value from there. So let's do an example together. All right, in the book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the NHL. Well, I guess rest in peace, NHL right now. But specifically, since January 1st is the cutoff for youth leagues in Canada, where many of the NHL players come from, players born in January will be competing against players up to 12 months younger than them. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it to the NHL, a random sample of 80 NHL players was taken. So we have a random sample here. We're going to have to do all of our stuff based on random sampling of 80. So a one-way table here shows that what they did was they said, okay, we'll just divide the birth months into 4 categories to make it easy. Now, I want you to see that this is just one set of 80, so one population. This is just one variable, the birthday, and it takes 4 outcomes. So it's not just looking at one proportion, it's looking at 4. So we took our 80 players and just divided them into their birth months. Do the data provide convincing evidence that birthdays of NHL players are evenly distributed amongst the 4 quarters of the year? Now, you have to think sometimes it won't be so easy to decide what your expected count should be. So we start by doing our null and alternative hypothesis. First, we don't have a significance level. We use alpha of 0.05. They asked us to test whether they're evenly or not. So the birthdays of the NHL players are evenly distributed versus an alternative, the birthdays of the NHL players are not evenly distributed. It's just that easy every time. It's not going to change how to do your null and alternative hypotheses. Expected counts. Now, before I show you on the next slide, I want you to think. If I had 80 players and we want to know if they are divided evenly or not, how many players would be in each of these 4 quarters of the year if they were so-called even? 20 each. 20 in each quarter. So our expected counts, you didn't have to do much calculating, but you see here as we go to plan step is still the same. You're going to name the test. Chi-squared test for goodness of fit. The data came from a random sample. Yes, there are at least 800 NHL players, and they tell us that there were 879 that year. Now, if birthdays are evenly distributed amongst the 4 quarters, the expected counts are each 20. So they got that by saying 80 evenly spread over 4 is 20. This is at least 5. The 3 conditions for inference are met. To calculate the test statistic, you take the observed minus expected, square it, divide by expected. And then you add up those 4 numbers together. We get an 11.2 chi-square statistic. We only had 4 outcomes. So our degrees of freedom is 3. 4 different groups, 3 degrees of freedom. The p-value for 11.2, if you're using the table, is between 0.01 and 0.02. Small. This is small p-value. We are going to reject. Because the p-value of 0.01 is less than 0.05, we reject H0. We have convincing evidence that the birthdays of NHL players are not evenly distributed in the 4 quarters of the year. Since our alternative was just even or not, don't tell me that it looks like more players were born in January in your conclusion. Just conclude what the alternative said, not evenly spread across the year. So that's it for section 1. Now, you're going to want to try and look in your calculator for this test as well. When you're doing this in the calculator, it's going to be called the chi-squared GOF test. If you don't have a TI-84 and you're using the TI-83, you are going to have to do this using tables in your calculator, meaning you'll do the stat edit. You'll put observed in one column, expected in the next column, and then you'll just do L1 minus L2, and then you'll square, and then you can store it in L3. Then you're going to want to divide it by the expected counts, which is your L2. So you'll do L3 divided by L2, and then you're going to have to sum up whatever column you put them in. This is going to be also explained in your textbook, so you're going to want to definitely reference 11.1 in the textbook. But if you have your chi-squared GOF test, you're also going to have to put this data into a list in your calculator. So the chi-squared GOF test in your calculator, I'm just pulling out my calculator now. Chi-squared GOF test is going to say, you're going to go to stat, you're going to go to tests, you're going to go down to chi-squared GOF test, and it's going to say observed in L1, and then it'll say expected in L2. Now, after you put your observed in L1 and your expected in L2, you're going to have to tell it what your degrees of freedom is. So your degrees of freedom here will just be 3. So for this one, we would have gone to Stat, Edit. In List 1, you're going to put your 32, you're going to put your 20, you're going to put 16, you're going to put 12. Those are your observed. In L2, you're going to put your expected, 20, 20, 20, 20. You're going to go to Stat, Tests. You're going to go to chi-squared, G-O-F, test. You're going to say degrees of freedom is 3. You're going to hit Calculate, and you'll see that it gives you the chi-squared of 11.2 and the p-value of 0.0106. The last thing it does is give you contributors. That's 7.2, 0, 0.8, and 3.2. That's basically saying which of the 4 categories contributed the most to the chi-squared value. That 7.2 shows that the January, February, March category contributed the most. See the 7.2? That's the first quarter contributors. So that's the reason we rejected the most, because there were more people in the first quarter of the year. It's called the biggest contributors to the chi-square statistic. So again, it's very hard. We're on the line with the video. I will keep posting things. You have to ask me questions. You can ask in the discussion board, but you want to also be following the calendar, doing homework, doing practice, and making sure you caught up on this video. Again, now you should be on to some practice. You should be doing your day 1 homework. All right, I'll check in with you guys in a couple.